Welcome everyone. In today's session, we are going to discuss about the topic surface integrals. Surface integrals of scalar fields. So in section 14.1, we have already discussed about Okay, in section 14.1, we have already discussed about the fact that the mass of a thin plate lying in a plane region can be found out by evaluating the double integrals. Right? Now, if sigma xy is a mass density of the plate, then instead of flat plate, let us suppose that now the plate is given of this type. Now our question is of this type means our question is how we can determine the mass of this plate. So as we adopted in the previous sessions, we are adopting the same method. That means we will have the projection of this over this plane and find a rectangle here. So we will divide this into so many rectangles and we will select one such rectangles and find some evaluation point, then find here, then we will find what's the area of or the of this Sij, some small portion, and then we will sum it up, and when we will say that this partitions become finer and finer, that means if your partitions is of mn partitions, then if m and n tends to infinity, what will happen to this one? That will we will first of all we will get the Riemann sum. Then as n and m tends to infinity, it will become a integration. So here too we are having the same thing. See, first of all we have found delta Sij, that's the area of the small portion, and we got it as, you can refer this in your surfaces classes, video of your previous class. Then you will get that this delta Sij is equal to square root of gxxy yj square plus gy xi yj square plus 1 into dA. We have done so many problems in that. Now we can say that the mass of this is approximately equal to, mass of this is approximately equal to density function into this volume, right? Now next what we're going to do is we will sum it up all together to get the entire mass, right? So this is the entire mass. Now this is going to be an approximation only. So to get a better approximation, what we're going to do is we'll say that this m and n tends to infinity. We will get this Riemann sum. When n and m get to infinity, we will get this as this integral. So the formula for finding the mass of a non-rectangular region is going to be this one. Now let us see, the derivation is not in your syllabus, so let us see directly to the definition and problems. Surface integral of a scalar function. Let f be a function of three variables, that means f of x, y and z, defined in a region in space containing a surface S. The surface integral of f over S is, so the surface integral we will write it as double integral over S f of x, y and z ds. That's equal to nothing but limit n comma m tends to infinity summation of this. That means it will become the double integral over S f of xy into ds. That is, ds means dx dy type. Now evaluation of surface integrals. If S is defined by z equal to g of xy and the projection of S into the xy plane is R. See here in figure 1, this figure, in this figure, you can consider here z is given in terms of a function of x and y. So when you're projecting this function to xy plane, similarly, when it's given this y as a function of x and z, where we want to project is in the zx plane. This zx plane. So whenever it's giving as a function of y and z, we want to project this to our zy plane. Okay. So S is defined as z equal to g of xy, and the projection of S onto the xy plane is then integral over S f of xyz ds is equal to integral over R over rectangle g of xy and square root of gx of xy square plus modulus of gy of xy square plus 1 into dA. So similarly, we can have whenever your y is going to be a function of x and z, and x is going to be a function of y and z also. So in each case, we are having the formula the same. Only difference is that we should give the cyclic changes in the formula in terms of variable. That means whenever you're finding with respect to z equal to g of xy is given, this every term should be in terms of x and y. See? And whenever you are defined by y equal to g of xz, then every term is of the form x and z terms. See? Instead of y, we should write g of xz. So here, gz is coming. No y term is coming. Derivative with respect to z is coming here. With respect to x is coming there. Whenever it's giving us a function of x and z. Only that thing you should note here. Now let us see. If we take f of xyz equal to 1, then the formula gives the area of that surface. Now here is one example. Evaluate double integral over s x ds, where s is part of a plane 2x plus 3y plus z equal to 6 that lies in the first octant. So what it means, we want to evaluate this is a part of the plane, right? So this is the picture. That plane is going to be as 2x plus 3y plus z equal to 6. Okay, in the first octant it lies like this. So we want to this is in yz plane, right? So we want to project that into xy plane. So in the xy plane we will get a triangle of this type. So we want to find the double integration. So we want to have the limit of x and y. For that only we are drawing this. Now can you suggest what is the limit of this? We'll get f of xy z dx dy, no? So what should be the limit of x? Here with respect to y is easy, so let me put it as dy dx. So y is ranging from this point to this curve. So from this, what you're getting is this is your equation now. In this case, z equal to 0, because you are projecting that to xy plane. So from this you will get 3y is equal to 6 minus 2x, or y is equal to 1 by 3 into 6 minus 2x, or that's equal to 2 minus 2 by 3x, right? So the y is ranging from 0 to 2 minus 2 by 3x, and here x is varying from 0, here 0 to 3. So this is the thing we want to calculate. Let us see. So we want to find double integral over s f of xyz ds, and that's equal to double integral over as x dx. Function is x dx. So x into ds can be written as square root of gx xy square plus gy xy square plus 1 into dA, where dA is dx dy, right? So see here, we're given everything here. Then when you are finding the limit for that rectangle is coming as from 0 to 3 and 0 to 2 minus 2 by 3x. That's the thing we have noted. See, 0 to 3 and 0 to 2 minus 2 by 3x. So we can easily evaluate that. So when you are evaluating this, first we want to integrate with respect to y. So integrating x with respect to y means you will get xy between the limit y equal to 0 to y equal to 2 minus 2 by 3x. Inserting the limit, we will get that as 2x minus 2 by 3x square. Again we want to integrate between the limit 0 to 3 with respect to x. You will get root 14 into x square minus 2 by 9x cube between the limit 0 to 3. By substituting the limit, you will get that as 3 into root 14. Next is here another problem. Find the mass of the surface S composed of the part of the paraboloid y equal to x square plus z square. See, it's from x square plus z square. So the picture is like this: y axis and z axis. It will lie like this. Between the planes y equal to 1. Y equal to 1 means it's a line parallel to your x-axis. So this is the point y equal to 1. See, the line may come like this. See, this line. It's the line y equal to 1. Y equal to 1. Then, and y equal to 4. So y equal to 4 means this is the line. Y equal to 4. Now, in between these two, what is the area they are asking? The density of the point P on S is inversely proportional to the distance between P and the axis of symmetry of S. So we want to take a point P and axis of symmetry. That is, axis of symmetry is y-axis. So distance from that point to y-axis only we want to say. Now this is our picture. So when you are projecting this to which plane? XZ plane, right? XZ plane, you will get two circles like this. So the solution is projection onto XZ plane, as I said, is shown in figure. Using equation 4, that is the formula, with f of xyz equal to sigma xyz, and we have given that is inversely proportional to square of that, right? See what's given statement: inversely proportional to the distance between P and the axis of symmetry of S. That means from P to this y-axis. So what is the distance connecting that point to y-axis? It's nothing but x square plus z square whole thing raised to 1 by 2, right? Since it is inversely proportional, see the distance from you're having x-axis, let me make y-axis and z-axis. So your solid is somewhere here. Somewhere here is your solid. Okay. Now you take any point and y-axis, the distance between point and y-axis. So if you're taking this point, means it is of x, y, z type, right? Now from this to here, the distance should be square root of x square plus z square, because y-axis when you're taking, this should be 0, right? So this thing only the distance. Now it's given that this is inversely proportional. That means your sigma is uh, proportional to 1 by square root of x square plus z square. So you can write this as sigma is equal to k into x square plus z square all thing raised to minus 1 by 2. Right? So that only they have written. Now where k is a constant of proportionality and y is equal to g of xz, that's equal to x square plus y square. Right? Now m equal to double integral over s sigma xyz ds, that's equal to integral over s k into x square plus z square all thing raised to minus 1 by 2 into ds. Using the formula, you will get y as h and square root of gx xz square like this. So that will reduce this as, so you can go for here the integration is x square plus z square is coming, so you can go for polar coordinate systems with x equal to r cos theta, and here now y is there, so z equal to r sin theta, and substituting we will get, and remember dx dy, this dA means dx dy, dx dy can be replaced with r into dr d theta. Right? Now remembering that, just you convert everything into polar coordinates, you get an expression like this. Okay. Now parametric surfaces. Hope you understood the previous problem. So parametric surfaces. If a surface S is represented by a vector form RUV equal to XUVI plus YUVJ plus ZUVK. If this type, when you are representing a surface, we will say that it is in the parametric form. Then with parameter domain D, then an element of surface area is given by du, it's given by modulus of ru duv cross rv uv dA. Right? Now this is going to be the surface area of an element. Then what we have to do to evaluation of surface integral for parametric surfaces means if S is continuous function in a region that contains a smooth surface S with a parametric representation, RUV is equal to XUVI plus YUVJ plus ZUVK, where UV belongs to D, then the surface integral of F over S is double integral over S f of xyz ds will become double integral over D f of RUV into modulus of RU cross RV into dA, where f of RUV is equal to f of XUV, YUV and ZUV. So whenever you are asking to evaluate the surface integral in parametric surfaces, what you have to do is first you should note what is your R. So RUV, what is that? Identify your XUV, YUV and ZUV. Then you find what is your partial derivative with respect to u of R, that is RU. Then partial derivatives of R with respect to V as RV. Take the cross product, then find the modulus, then substitute in this integral. So let us see one problem. Evaluate double integral over S x minus y by square root of 2z plus 1 ds. So as I said, from where you should start, you should pick up the vector form of that integral. So that means this one, RUV is equal to, okay, so this is your key role. So from where we should start? We should start from RUV. So given that RUV is equal to U plus VI plus u minus vj plus u square plus v square into k. So this is, you can compare with x uvi plus y uvj plus z uvk. So you can have x of uv is equal to, what is that, u plus v, and y of uv is equal to u minus v, and z of uv is equal to u square plus v square. So we have identified all the x, y and z here. Now what I said next? Next we want to find what is your ru. So derivative with respect to u we want to find. So derivative with respect to u of ruv is, what is coming here? This is your ruv. So ruv with respect to u. So first case u into I, that is I. Second one again plus j. Third one plus 2uk. Similarly, you want to find what is your RV. So RV you will get it as I minus j plus 2vk. Now we want to take the cross product. See here, RU cross RV. So determinant ijk. Then find the coefficients 1, 1, 2u. So then 1 minus 1, 2v. And find its determinant. So you got it as like this. So this is a RU cross RV. Now we want to substitute in this formula. Now substituting in the formula, take care that here x and y are there. So instead of x and y, you should substitute this. Right? X substitute with this, y substitute with this, and z substitute with this value. Then your ds will become, see, cross, I should find its modulus also. I forgot to tell that we should find the modulus of the cross product. So we'll get it like this. You know that when a vector is given xi plus yj plus zk, modulus is going to be square root of x square plus y square plus z square. So in the same way, therefore double integral over as x minus y into square root of 2z plus 1 ds, that's equal to integral 0 to 2 integral 0 to 1. Very good, this intervals 0 to 2 and 0 to 1. See, given u is changing from 0 to 1 and v is changing from 0 to 2. Now as I said, we want to replace x with x of uv. So I have replaced that here also. Then in the expression you will get it as, see here means these two terms are going to be the same, right? So you can cancel it. So only one 2 will be the, from here you will get 2v. So altogether 4v. So 4 into v with respect to du dv. So you will get 4 into integral 0 to 2 uv dv. And integration, it will result as 8. Hope you understood this problem. Okay. Only thing is here we want to notice that we want to identify x uv, y uv and z uv. Then you want to find ru, partial derivative with respect to u of r, and partial derivatives of r with respect to v. Take the cross product of that. Then take its modulus and substitute into our formula. Our formula is this one. Double integral over as f of x y z, surface integral in parametric surfaces. I am saying double integral over as f of x y z ds is equal to double integral over d f of ruv into modulus of ru cross rv into dA. Now substituting and simplifying, you will get the surface. Now here is special surfaces, that means oriented surfaces. Oriented surfaces means, suppose you have got a surface here, some sphere or something, right? Now I can have a point over in this sphere here or here. Now I can give the direction like this. So every point in the sphere I can have a give a direction like this. This direction is called orientation. Now in the same way I can have the direction in the opposite also. That means in this direction. That means inward. So we will say that, see here, in this sphere, this n and minus n I have marked. This is called outward and this is called inward. So in general case, we will say that the outward direction is our orientation. You can read this. A surface S is orientable or two-sided if it has the unit normal vector n that varies continuously over S. That is, if the component of n are continuous at each point xyz on S. Now any closed surface that are boundaries of solids such as spheres are example of orientable surfaces. That means you can give a unit normal here. See, normal vector n that varies. So it's a unit normal vector. If you can give a unit normal vector to a surface, we will say that that is orientable surface. And in general cases, we will get, if the surface is of connected one, you will get exactly two orientations here. Now the unit inner normal that points inwards from S and the unit outer normal that points outwards from S. By convention, the positive orientation for a closed surface S is the one for which the unit normal vector points outward S. That means this is called a positive orientation. And this one is called negative orientation. Now there are surfaces we cannot give this orientation also. Okay, such one example is the Mobius strip. Some of you know how to create a Mobius strip. Only thing is that take a strip of paper, just twist it and paste at the ends. Twist it and paste at the ends. So you get a figure like this. Now this Mobius band is not going to be orientable. Because see here you can give two directions, this side and this side. But when you are traveling along this Mobius band means one can travel in this fashion. From here starting and see from here onwards he will enter inside it. See? Now I can walk from here, from its outside also. Right? So I will reach here. That means this surface is got only one face. Okay, let us see one short video of this. See, here the man is walking around the Mobius strip. See, he is starting from this direction. Okay, now you can see this man can easily enter inside of this Mobius band. See here, he is walking. See, he has reached inside. He started from outside. Now he is in inside. Now the same way he can come. See, outside also. Now he is in outside. So that's the thing. We cannot give Mobius strip two-way orientation. That means we cannot give from the orientation as our normal definition. We cannot give such a orientation to Mobius strip. So Mobius strip is an example of non-orientable surface. So example of a non-orientable surface is the Mobius strip. So with this, I'm winding up the session here. Thank you for your patient listening. Thank you.